We set up the notion of type checking with the idea of a check function that would take an expression and return true or false, say true is okay to interpret, false is not okay. But we've discovered that we actually need a type check function that takes an expression and gives back a type so that we can deal with sub-expressions and arrive at a conclusion on whether something is okay. So we're not going to have a checking function at all. Instead, we'll just have type check. If it does give you back a type, that's like true from check. It means it's okay to interpret. Otherwise, type check will raise an exception. It won't give you a type back. The expression has no type, and in that case, it's not okay to interpret the expression. Notice that it's expressions that have types, not values. The word type is used in different ways, but in this class, if you try to get the type of a value, then you're doing it wrong, because we're type checking before interpreting, and that means we have expressions, not values. Before we go off and write this type check function in Shplait, we're going to sketch the type check function, temporarily calling it colon, because this is one of the traditional names for the type check function. So here the colon operator takes an expression on its left, and it returns, its return value is shown on the right. For example, if we have the expression 1, its type produced by the type check function will be int. If we have the expression 2, its type will be Boolean. And so we don't get specific integers back or specific Booleans back, we just get this type as a bit of syntax, in the same sense that 1 is a bit of syntax as an expression, int is a bit of syntax as a type. For something more complicated, like 1 plus 2, the type check function on this needs to recur and type check the left-hand side and the right-hand side. In both of those cases, 1 and 2 will be given type int, and plus will be happy with this. So it'll say, okay, the type of the whole expression is int. On the other hand, if you have a plus expression with 1 and false, we type check the left-hand side and get int, that's okay, but when we type check the right-hand side, we'll get Boolean, and so type check for plus will say, no, that's a problem, it'll raise a no-type error, so it will not be okay to try to interpret this program. To write out those kinds of compound rules, though, we start with our basic rules, like any integer has type int, each of the two Booleans have type Booleans. For plus, we can write the implementation this way. You read the bottom as the input, the goal here. So if we're trying to get a type for some expression plus some other expression, then what we do is above the lines are kind of like recursive calls. So to get the type of this plus expression, we recursively get the type of the first expression. And if that is of type int, then this part will match. We get the type of the other expression. If that's of type int, then this part will match. And if all of these pieces match, then we will be able to say int is the result. So if we just have the expression 1 and we apply the rule, we directly get integer back. If we have true, we apply this rule here and directly get Boolean back. If we have 1 plus 2, we try to apply this rule. So x per 1 matches to 1, x per 2 matches to 2. If we look at x per 1's type, well, that matches this rule here, so we get the integer back. And similarly, when we type check the expression 2, we get integer back. That all matches as expected in a rule, so we are allowed to supply the result type int there. On the other hand, if we tried to match everything here, when we type check false, we would have to use this rule, we'd get Boolean. Boolean does not match int that our rule says is there, and so it's not that we return no type, it's just that we can't make this tree matching that tree. And we can make deeper trees. So if you have 1 plus 2 plus 3, then you type check 1 plus 2, and you also type check 3. Meanwhile, we saw how 1 plus 2 goes. In any case, we get some expression with int here, so it matches that part. An expression with int over here matches that part, and that's why we're allowed to put int at the bottom. So these trees show a kind of trace the application of these rules, and that's why it's a nice notation for writing down type systems. Just like we define what parse does with a grammar, we define what type check does with these rules, either the immediate rules or the compound rules with the horizontal bar like this.